C infinity category. Okay? Now, there's a little problem here because EG is infinite dimensional. So EG is not a manifold. It can be approximated by finite dimensional manifolds, like S infinity can be approximated by finite dimensional spheres. Okay? But what we're going to do is to construct an algebraic model for this. So it doesn't matter that it's infinite dimensional. And we're going to construct an algebraic model using differential forms. Okay? And so the differential forms on the base pulls back here, and they are called basic forms here. Okay? So today I want to characterize basic forms. Now, basic forms has two properties, one of which is that it's invariant. So first look at invariant forms. So we can look more generally at the situation when G acts on a manifold N. Let's say on the left. Okay. Then each G in G defines the diffeomorphism LG, which is multiplication on the left. Okay? And then we say that a form is invariant a form omega is G invariant if LG star omega is equal to omega for all G in G. Okay. Now, when G is connected, then we have this theorem that characterizes invariant forms. So suppose G connected, so a form omega on M is G invariant if and only if the Lie derivative of omega with respect to A bar is 0, okay, for all A bar in little g, which is the Lie algebra of the Lie group G. Okay? So we proved this in one direction last time. I think we proved it in this direction. That's the easy direction. Okay. And now we want to prove it in the other direction. Okay. So suppose LA bar omega is 0. Okay? Now, so let's look at, let's first write down what this means. Okay? Now, to calculate the Lie derivative, you need the integral curve of the vector field. So let P be a point in N. Okay? And we know that an integral curve of A bar through P is phi t of P is equal to. Okay, now do you remember that? What's an integral curve of this vector field? So A is an element of the Lie algebra, and on the manifold is going to give you a vector field, okay, which we call A bar, and through each point P you have an integral curve. Okay? Yeah. So do you remember the formula for the integral curve? Yeah, it is e to the minus TA. That's an element of the Lie group applied to P. Okay? And this is left multiplication by e to the minus TA. And yeah, so phi t, that's your integral curve. And so by definition, the Lie derivative, it's, let me see, you, at P, right, yeah. For a form, it's easy, right? You just pull back. So it's phi t star of omega. You pull it back to P, and then you take the derivative at time 0. Okay? So that's the definition of the Lie derivative. And so it's d dt, and phi t is L e to the minus TA star of omega. Yeah. And so by definition, this is 0. Okay? This derivative is 0 at time 0. Yeah. Now, what we like to show is that this, let me see, we like to show that omega is left invariant. Yeah. So we like to show that this is constant. Oh, sorry, this is at P. We like to show that for all t, this is constant, omega. Okay? So let's define h of t to be this expression at P. So it is a function of R, and let me see, what's the target space? The target space is, let's say this is a K form. Okay. So it's a K form at P. Okay. So the target space is in lambda K of the cotangent space. Right? It's a finite dimensional vector space. Okay? And so what we want to show is that H is constant. Okay? Okay, that would prove that omega is left invariant under these group elements, okay, under the exponential. But what can you say about a connected Lie group? There's a theorem about a connected topological group. Pardon? The exponential map is always surjective in a neighborhood of the identity. Okay? It may not be surjective globally. Okay? It's the exponential map is a diffeomorphism in the neighborhood of the identity. Because why is that? Why is the exponential map a diffeomorphism?
By inverse function theorem.
Pardon?
Using inverse function theorem.
Yeah, by the inverse function theorem, because the differential of the exponential map is what? Identity. It's the identity. So it's non-singular. And by the inverse function theorem, that says that the exponential map is a diffeomorphism in the neighborhood of the identity. Therefore, it's surjective onto a neighborhood of the identity. Okay? That's true for any Lie group. But if you have a connected topological group, then what can you say about it?
It is generated by any open neighborhood.
Yeah, it is generated by any neighborhood of the identity. Okay? So that means every element in the Lie group can be written maybe not as an exponential, but as a product of exponentials. Okay? So if you can show that omega is left invariant under an exponential, and the Lie group is connected, then it will be invariant under all Lie group elements. Okay? So we need to show that h of t is constant. Okay, so if it's constant, then it's equal to h of 0. And h of 0, that's the identity. So h of 0 is omega of t. Okay, so we need to show that this function of t is constant. Okay? Now, how do you show that a function of t is constant? Yeah, you differentiate, right? And show that the derivative is 0. Okay? So we differentiate t. You see, here we only know that the derivative is 0 at 0, right? But we need the derivative to be 0 everywhere. So if you differentiate at t, that means you move t a little bit, say by s, and then differentiate with respect to s and evaluate at s equal to 0. So you move t a little bit, so it would be L e to the minus t plus s a star omega. Okay? So that's the derivative at t. And yeah, the exponential has this property, right? It's multiplicative, so it's L e to the minus t a star e to the minus s a star. Okay? Here, it doesn't matter what the order is, right? Because you can switch s and t. Omega. Okay, now, it's the whole thing at p, so that means if I pull this back, it would have to be e to the minus t a dot p, right? If I pull this back by this, it will be at p. Okay? Yeah. Okay. And now, I can interchange these two, right? Why can I do this? Okay, why can I pull this out? Well, I mean, it's because this guy is, what is so special about this? It's the pullback of differential forms. I'm looking for one word. This has a property that allows you to do this. Yeah. No, the pullback commutes with the exterior derivative, but we don't have the exterior derivative here. Well, you see, if you write out the definition, this is a limit as s goes to 0 of L e to the minus ta star L e to the minus sa star omega minus L e to the minus ta star omega over t over s, yes. Okay. And the thing is, this, it's linear. See, because it's linear, you see, you can write this as L e to the minus ta star, okay, L e to the minus sa star omega minus omega over s. Okay? And then, this is linear. So, for a linear function, you can interchange the two, right? Because a linear function is continuous. So then this limit comes inside and you get this. So this is because L e to the minus ta star is linear. Okay? So if you have a linear map, it commutes with the derivative. And can you tell me what this is? Tell me what this is. Huh? It's what? It's zero. Why is it zero? This is the v derivative of omega with respect to a bar at the point e to the minus ta dot p, right? But the v derivative is assumed to be zero everywhere, so this is zero. And so equals 0, okay? Yeah, so this proves that h of t is a constant. Okay? And so h of t is L e to the minus ta dot p, star omega at p, right? At p. So, but since G is connected, okay, every G in G is the product. Well, let me put it this way. Yeah. Since G is connected, G is generated by any neighborhood of the identity. And there is a neighborhood U of the identity such that the exponential map from the Lie algebra to the Lie group surjects, well, let me see, is a diffeomorphism on U. And so every G in G is a product of finitely many exponentials. Okay? And since omega is invariant under any exponential, so it's invariant under any G. So this is true, yeah, for all P, for all G in G and P in M. Okay. And yeah, so this proves the other direction. Okay. So we now have a characterization of invariant forms. Now, okay, there's another property of basic forms, and it's called horizontality. So, okay, to define horizontality, I have to okay, I've already defined vertical. Let pi, say from E to M, be a fiber bundle. So with fiber F, and suppose P is in E, then the differential from the tangent space P to the tangent space of pi of P, okay, is surjective. And the kernel is what we call the vertical vectors. Vp is the kernel of pi star. It's the vertical vectors. At P. Okay. Now we suppose we have a principal bundle. This principal G bundle. Okay. And we can JP from the Lie group to P by JP of G is P dot G. Okay. Okay. And then let's compute the differential of JP. So, if A is in the Lie algebra, that's the tangent space at the identity. Okay. Then JP of A is equal to, now to compute the differential, you can use a curve. So you take the curve, e to the TA, times P, right? E to the TA is a curve, yeah, through the identity with initial vector A, and then, then you apply JP to it, and you differentiate. Okay, so that's how you calculate the differential. And therefore, this is d dt t at t equal to 0 of P dot e to the TA. And what is this? Yeah, it's a fundamental vector field at P. Okay? Sorry, there should be a lower star here. I want to compute the differential of JP. So the differential of JP actually gives you the fundamental vector field. And we know that this is a vertical vector. The fundamental vector field is a vertical vector. Okay? Yeah. So JP star goes from the Lie algebra into VP. Well, I claim that this is injective. You see, claim if A is in the Lie algebra and the fundamental vector field has a 0 there. I think let's do an if and only if. So let A be in the Lie algebra. Then the fundamental vector field has a 0 if and only if P is a fixed point of the curve e to the TA in G with T in R. Okay. Now, in one direction, this is easy because A bar P is ddt e to the P times e to the TA, evaluate at t equal to 0. And if you have a fixed point, then you are just differentiating P. So if P is a fixed point, e to the TA, and then this would be 0. Okay? So if you have a fixed point, then of course the fundamental vector field will vanish there. Okay. Now let's prove the other direction. So suppose the fundamental vector field vanishes. Okay, now, what's an integral curve of the fundamental vector field through P? An integral curve of A bar through P is phi t of P is equal to, it is this, right? P dot P to the TA. Okay? But if the vector field vanishes at P, can you see another integral curve through P? There is another integral curve through P. Pardon? The constant map. You see, let C of P be the constant map P. Okay? Then the derivative is 0, but 0 is A bar P, and this is A bar at the point C of T. So that says that C of T is an integral curve of A bar, and C of 0 is P. Okay? So, C of T is another integral curve of A bar through P. Well, now you have two integral curves of A bar through P. How can that be possible? See, integral curves are unique, because they are solutions of differential equations. And you have two integral curves now. So that means they're equal. So by the uniqueness of integral curves, phi Tp is equal to P for all T. Okay? And that proves that P is a fixed point of e to the TA. Yeah. All right. Okay, now, so tell me now, what can you say about this map? This map. What can you say about this map? The differential of JP. Um, um, let me see. So if let's see, if it's 0, I want to say that it's injective. Yeah. It's going to be an isomorphism, but like these have the same dimension, right? Because this has the fiber dimension of the principal bundle, so the fiber dimension is the dimension of the Lie group. So these have the same dimension, and so if JP, let's see, I thought I had it earlier. So if this is 0, well, that means A bar P is 0. Then P is a fixed point, e to the TA. Yes, but how does that say that A is 0? Pardon?
Because the P is principal to
Yes.
so you can have the JP is the right action. You must have free.
Oh.
So you can have this.
Oh, right, yeah. So P is a fixed point of TA. That means the stabilizer. Yeah. So the stabilizer of P is includes e to the TA. Yeah. But because P is a principal bundle, G acts freely on it. So the stabilizer of every point is just the identity. So since P is a principal G bundle, G acts freely on P. So the stabilizer of any P is just the identity, okay? And if A is not the identity, you are going to get a whole curve. If A is not 0, yeah, you get a whole curve, yeah. So, yeah, e to the TA, this has to be just the identity. And the only way that is possible is when A is 0. Okay? And so, yeah. So J star, JP lower star from G to VP is injective. And since the dimension of G is equal to the dimension of the V group, and that's the dimension of the fiber, JP lower star is an isomorphism. Okay? So that says every vertical vector is of this form, A bar P. Okay? Yeah. So thank you very much. You saved me. Yeah. Yeah. Mm-hmm. Yeah, I taught this course 3 times, in the United States, in Pakistan, and in Taiwan. Now, in the United States, sometimes, I have students who can save me. In Pakistan, they're all quiet. They never say a word. And here, I'm glad that, you can sometimes help me out. Okay. Okay, so now we know what the vertical vectors are. They all look like this, A bar P. Okay? And now, a basic form has the property that when you apply it to a vertical vector, it's 0. Let me see. I have some time. So these are called horizontal forms. So let pi be a fiber bundle. So a form omega on E is horizontal if at any P in E, when you apply omega to a vertical vector, you get 0 for all y, okay, a vertical vector. Now, you see, basic forms are horizontal. Because basic forms is a pullback of something. So IYP omega, and then let's say omega is a K form. So suppose omega is a K form on E, and then V1 to Vk minus 1 are tangent vectors at P. Then you apply IYP to omega, and that means the first argument is yp. Okay. But omega is the pullback of tau. This is omega at p. And then, what's the definition of the pullback? What's the definition of the pullback? How do you calculate the pullback? Yeah, you take tau at pi of p, and then you push forward. The vectors, but because y is vertical, the push forward is 0. Okay, so equals 0. Okay, so the pullback has two properties, right? So the basic form has two properties, basic forms. And here is the theorem. The theorem basically says that basic, now we already know that basic implies invariant and horizontal. And the theorem says that the converse is also true. Okay? If a form on a principal bundle upstairs is invariant and horizontal, then it's basic. Okay, so I will prove this in the next hour. And I also will do an example of computing the ring structure on the cohomology of the total space. Okay, like I will do it for U2, and then, in the homework you do it for UN. Okay? All right, so let's take a break for 10 minutes.